Hey everyone, we're looking at class number 6. Hopefully the camera looks pretty good. The reason I'm doing it this way is because we're going to be using some protractors and rulers. Maybe I'll even put class 7 in the same video. So I'm going to go through the notes part quickly here. I really just want to focus on the drawings because that seems to be where people had questions. So just a quick review. A vector has both a magnitude and a direction. The examples we spoke about last class were displacement and velocity. Scalars have a magnitude, but not a direction. Distance and speed are examples of those. So if we look at these 4 options below, which are vectors, it needs a magnitude and a direction. So we'd have the first choice here, 50 meters per second is our magnitude, east is our direction. And we'd have 1.7 miles per hour to the left. 1.7 miles per hour is our magnitude, left is our direction. Just a quick little list of scalars and vectors that you might think of. So we have displacement, speed, but some others that you might not really think about. Mass has no direction, but it has a magnitude, right? Like 5 kilograms, but you're not 5 kilograms up, down, left, or right. Volume, you don't have 50 milliliters west. Temperature, again, you don't have 5 degrees north. And time, you don't have 4 seconds down. Okay. Vectors, on the other hand, you can kind of put a direction behind them. Sorry about this for a second. Sorry. This first one should not have been displacement. It should have been distance. Vectors, on the other hand, it makes sense if you put a direction behind them. So we have displacement. We have velocity. We have force. Now, force, think about it. If you're pushing with 5 newtons east, pushing with 5 newtons left. Okay, so the direction there matters. Other examples of vectors are things like fields, like not like fields of grass, but like magnetic fields, electric fields, gravitational fields. Those all have directions to them. Gravitational. Okay. So one thing I emphasize when we do vectors as a class is it's kind of an iterative process. We cover it in a variety of ways, and over time, they start to make more and more sense. So if you get a little bit confused at the beginning, that's okay, that's normal, that's expected. As we move forward with it, it'll start to make more and more sense to you and become clearer and clearer. So adding and subtracting vectors. Scalars can be added and subtracted just like any old numbers. Vectors, on the other hand, cannot be added and subtracted in any old way, and that's where we're going to kind of start a discussion of vectors. But first, well, what is a vector? How do I draw a vector? What do they look like? Okay, so we can actually draw vectors. And the nice thing about vectors is they're extremely easy to draw. If I want to represent 3 meters per second east, all I do is draw an arrow 3 meters, not 3 meters per second, just 3 meters east. The size of it is 3 meters. The direction is east. If I'm representing it as 8 meters east, it still points to the right. It's just a little bit bigger. Now, we're not drawing it to scale right now, but if we were, it would be exactly, I think it's 2 2/3 times bigger. But for now, it's just bigger and still pointing east. C asks for 12 meters per second east. So it's still pointing east and it's 12 meters per second. Now, if you were to draw 6 meters per second west, it should be half the size of this vector, and west is pointing the other way. Now, meters per second and meters, you can't really compare the size of those vectors. Those are just 2 different things altogether. Okay, you can only compare like units. So let's say I asked you to add vectors. Let's see. I want you to add vectors from 4a and 4b, so these two right here. And since they point in the same direction, we say they're added at 0 degrees. So let's just set it up like we would a math problem. We have 3 meters plus 8 meters equals. So before we get to the equals and what it looks like, I just want to emphasize we always add vectors tip to tail. What does that mean? This is the tip of the vector. This is the tail of the vector. So you always line them up tip to tail. It does not matter which one you put down first. That will work left to right here. Never tip to tip. Never tail to tail. So if I draw it out, 3 meters. Now I start at the tip of this vector. I'm going to put the tail of the 8 meter vector going the same way. Do not change the direction of the vectors. They both point east, so keep them pointing east. Don't start here and then draw the 8 meter vector going the other way. Draw the 3 meter vector and then start from there. Draw the 8 meter vector. Now, when you add the two, in regular math, we call it the sum. In vector speak, we call it the resultant, the resulting vector, which would start from the tail of the first vector and go to the tip of the second vector. So this is our resultant vector, this 11 meter vector going to the right. Okay, so if we flip over, there's some more to write about that. The resultant vector is the vector sum of the two vectors. It starts from the tail of the first vector and ends at the tip of the second. So this is our resultant. Again, this vector down here. So there were some really good questions that came up in class. There was some confusion about what's magnitude, what's resultant, what's displacement. Really good questions. So let's try to clarify that right now. When you add two vectors, the sum you get, we call that the resultant. It's just a general math term. Okay. The magnitude is how long it is. In this case, 11 meters. Now, that has to measure a physical quantity in our class. That physical quantity that it's measuring is displacement. If, for example, this was 3 meters per second and this was 8 meters per second, the resultant would look the same. It would be 11 meters per second. The magnitude would be 11 meters per second, but it would no longer be measuring displacement. It would be measuring velocity. Okay, definitely a little confusing. Takes some getting used to, but just keep in mind that when you add two vectors, what you get is the resultant. Okay, that's just math speak. Adding vectors, you get the resultant. If those vectors you're adding measure displacement, what you get is displacement. That's what the resultant is. And the magnitude is the size of the vector. Okay? Now, subtracting vectors. You will rarely ever be asked to subtract vectors in this class. We'll just talk about it briefly. So it says subtract the vectors from 4a and 4b. We say they are added at 180 degrees. Sorry for the sound in the background. There's some drilling going on outside. So we say they're added at 180 degrees. It's like adding 3 meters east to now 8 meters west. Basically, you just have to flip one of them. Sorry, there's a lot of sound outside. So think of it like this. Subtracting is adding a negative. So how do we do this? So the first thing we have to do here, we're going to draw our 3 meter vector. Okay, and we are going to add, we're not lining them up tip to tail yet, our 8 meter vector, but we're subtracting it. So we have to flip it. It's like adding 8 meters west. So it's going to look something like this, going the other way. So how do we add vectors? We draw the first vector, 3 meters. Actually, I'm going to do this over here a little bit more. 3 meters. So this is our starting point. Sometimes it's nice to mark the starting point. Maybe I'll get in the habit of doing that. Then we go to the tip of that vector, and that will show our 8-meter vector. It's got to go to the left, though, because that's the direction it points now, because we're subtracting it. So we're going to go this way, 8 meters. This is our ending point. So if you draw a line from where you start to where you end, that's our resultant. Okay, it's 5 meters. And you could say it's west. Sorry, I had to squeeze that in there. Okay, so that's our resultant there, 5 meters west. You're not frequently going to need to subtract vectors in this class. I figured we should show it. But if you're adding vectors at 180 degrees, that's going to be subtracting, basically. We'll see a lot of practice of that. I just wanted you to see it once here. Okay? And you want later on to be the first time you see it. So number 7 says, so far we've only added and subtracted vectors in 1 dimension. Let's talk about 2 dimension. So it says here, little Donnie walks 3 miles east of north. Let's just change that to northeast at 45 degrees to make it easy. Then he walks 3 miles east. Find his distance. His distance is easy. That's the total length of his path. So his distance is 6 miles. All right. But we need to find his displacement as well, and we're going to do it graphically. So here is his 3 miles northeast. Here is his 3 miles east. We need to physically measure those. So what I want you to do is take a ruler and measure this vector. This vector is 5 centimeters long. This vector is also 5 centimeters long. Makes sense, they're both 3 miles. So let's label those. This is 5 centimeters. And this is 5 centimeters. I like to label them in both centimeters and miles. So now you need to make your scale. 5 centimeters equals 3 miles. We can use that, but let's kind of simplify it. If I divide both sides by 5, that cancels. And I get 1 centimeter equals 0.6 miles. Okay, so that's our scale. We're going to come back to that in a little bit. So the next thing we're going to do, so we established our scale. We just used a ruler and measured it. We knew that these were 3 miles because the question tells us that. 5 centimeters, we measured that physically. So it says here, in the box below, line the vectors up, tip to tail. It doesn't matter which you do first. Addition is commutative. So I'm going to put a line right down the middle here. So here's what I'm going to do. I'm going to mark off my starting point. I'm going to do this question twice. Do it 2 different ways. The first way, I'm going to draw this vector first, then this one. Okay, so let's try that out. So in order to draw that diagonal vector, I need to create a 45-degree angle. All right. So how do I do that? I take my protractor. I put the little circle, this little circle here of my protractor. I put it right on my starting point. And I try to make the black line of my protractor parallel to the bottom of the page. Then I just measure up to 45 degrees. That's about right here. You see 40, 50, 45 is right in the middle. I'm just going to put a dot there. Now I'm going to draw my 5 centimeter vector from my starting point toward that dot. It might not reach the dot, and that's okay. That's just kind of my target line, if you will. And I'll label it 5 centimeters, 3 miles. Now I'm going to draw my next one. So they're doing a lot of work upstairs. I don't know what they're doing right now, but oh well, I'm in the school right now. Should have gone home. So now we're going to draw a 5 centimeter vector going straight east. So let's label that as being 5 centimeters. but also 3 miles, just to keep track. We're going to draw our resultant now, the sum of those two vectors, which will represent the displacement here, from start to finish. The arrow direction matters. The arrow goes from where you started to where you ended. You can make it a dotted line, a different color if you'd like. This is about 9.3 centimeters. I'm going to do it the other way as well. I'll do that right away. So I'm going to draw a 5 centimeter vector going straight east. And then a 5 centimeter vector going at a 45-degree angle. Now you can try to eyeball the 45-degree angle, but I would highly recommend you just take a minute, put a guiding spot there so you can make a nice 45-degree line. So if you're wondering, there's actually metal falling out of the ceiling right now, so I'll keep you guys updated on what's going on, but I don't know what they're doing, but they're doing a lot of work. So we're going to label this as being 5 centimeters. This is also 5 centimeters, or 3 miles. This is also 3 miles. Okay? If we draw a vector arrow from where we started to where we ended, it should be roughly the same as the last one we have, and it's almost identical. It's almost exactly 9.3 centimeters again. All right. So again, draw in your resultant on each. All right, so I just paused the video for a second because it got pretty loud. But here we are, we have our two vectors drawn here. All right, now we need to find the displacement. So the displacement isn't actually 9.3 centimeters, right? We need to now use our scale. All right, so we're back from a little break from all the drilling, hopefully for at least a few more minutes. So you have to use your scale to find out. Oh, there we go. All right, so we're back again. So real quick, just to finish up, to find the actual displacement, the magnitude of the displacement, right, the resultant vector is magnitude. We have 9.3 centimeters times our scale factor, which is 0.6 miles over 1 centimeter. Okay, how exactly do you know to put miles on top and centimeters on the bottom? You want the centimeters to cancel. It's always what you want. We want miles over what you have, centimeters. You throw that in your calculator. Throw it in your calculator and you get 5.6 miles. Now to measure the angle real quick, you always measure, or usually measure with respect to the imaginary x-axis. So you're going to take your protractor, put the middle of the protractor right on that little nub there, hold the black line parallel to the bottom of the page, and measure to the resultant, in this case about 22 degrees. Now what direction is that, 22 degrees? Well, if this direction to the right is east, this is north of east, all right? This angle would measure the same as well. All right, so this angle is equal to this angle.